Good morning, Neston U3A, Earth and beyond. For the last 15 to 20 minutes or so, we've been watching cosmic rays. And if I waffle for the next 30 seconds, we may be lucky enough to actually catch another one come through before we... You see that one? Yep, that's like a contrail made by an aircraft. This is a cloud chamber without water. This is with alcohol rather than water, which you get in the atmosphere, of course. But the same principle applies. A charged particle going through can actually trigger the condensation and leave yourself a condensation trail of droplets. And this will happen whenever a charged particle comes through. Some of those charged particles might have been generated by the Earth. Some of those charged particles might have been generated beyond, which is why I thought this talk was a particularly appropriate one for this group. So we'll be coming back to the cloud chamber. This is the cloud chamber itself sitting on the front bench. That's what you're actually looking at with the, here I've got the phone pointing at the cloud chamber. If you're interested in building a cloud chamber for yourself so that you wanted to see radiation, if you wanted to see cosmic rays, not only have I got the slides of the talk here printed out, also I've got the instructions for how you can build yourself a cloud chamber on your kitchen table, which is precisely what I did. Cost a few tens of pounds to build one of these. Okay, so let's start the talk proper, otherwise we're going to be here all morning. So what I'm going to be covering this morning is a little bit of background, because rather than talk immediately about cosmic rays, I think it helps to just give a little bit of context and talk about radiation from the Earth. Radioactivity, alpha, beta, gamma radiation. Then I'll talk about cosmic rays. They were discovered more than 100 years ago now. And I'll be talking about how they are detected. Different types of detector, including the ones on the front bench here. And then I'll finish with, right, these charged particles come from somewhere. If they're cosmic, exactly what are the origins? What are the sources of cosmic rays? What objects out there in the universe are producing charged particles which rain down on the Earth and allow us to either listen to clicks in a Geiger counter or see tracks in a cloud chamber. Then I'll summarize at the end. So just to make it clear, the U3A lawyers insist that I say I do have some radioactive samples on the front bench here. I'm going to use those in a demonstration shortly. But the radioactive samples, they're just naturally occurring elements. And at the end of the demonstration, I'm going to put those away to one side and invite you to take a closer look, if you so wish, at whatever's going on the front table. In front of me, I have a Geiger counter, which is currently clicking, and I have the cloud chamber. And I'll be explaining how those allow us to see or hear charged particles in due course. So we're listening to something clicking. It's a Geiger-Müller tube. Well, physicists call it a Geiger-Müller tube. Everybody else in the universe calls it a Geiger counter. So we'll just stick with the colloquial and just refer to it as a Geiger counter from this point on. So each click signals the arrival of a charged particle. Where did that charged particle come from? Well, it might have come from an atom lurking somewhere in this room. And yes, there are radioactive atoms in this room. I can pretty much guarantee it. But it's also possible that the click signals the arrival of a charged particle from elsewhere in the cosmos. Perhaps it started its journey in a supernova, somewhere in the Milky Way. It's always possible that one of those clicks signals the arrival of a charged particle that started its life in the jets of a supermassive black hole in another galaxy altogether. So these are genuinely cosmic. We can't tell from the click. The click just tells you something has arrived. If we want to tell what it is that's arrived, we need a different type of detector, and we'll come to that in due course. So let's deal with background radiation first. And just for the second, let's kill the annoying clicks. So radiation is around us all the time. Basically, you've lived with it all of your lives, and it's not necessarily something to fear. Before dealing with cosmic rays, let's just make it clear that the most radiation that you've probably thought about, given that you haven't thought about cosmic radiation, I would guess, most of the radiation you've heard about probably comes from the Earth, because the Earth is a radioactive planet. It's nothing to do with what mankind has been doing for the last few decades. the Earth has been radioactive for all of its 4.5 billion year history. It was radioactive when it was made, and it's still radioactive. And that's a consequence of some of the elements in the periodic table being unstable. So what do I mean by that? If we look at all of the 100 or so elements in the periodic table, some of them are stable in the sense that once you make an atom, that particular atom remains essentially unchanged forever. Whereas there are some elements in the periodic table that are unstable. Once they are made, they don't like being what they are. They want to change into something else. They want to move from one place in the periodic table to a different place in the periodic table. They want to change. Physicists talk about an element or an atom decaying into another atom or another element. Now, decaying doesn't mean basically sort of starting to go moldy. It means changing from one position in the periodic table to another. And we can visualize that in a number of different ways. Let's take an example. Let's take radioactive uranium. So that's what we're going to do. So we're going to switch back to the live demonstration here and look at radioactivity. Now, to start with, we're going to have a look at a particular radioactive sample. This is the radioactive sample. It's a piece of glass. It's a piece of uranium glass. People put uranium, or people used to put uranium, in glass. Did they do that to make the glass radioactive? No, they didn't do it for that reason. They did it for the reason that it makes it fluorescent. So uranium doping of glass means that if you put this in your glass cabinet and have some LEDs, UV lighting around the edge, you get a beautiful display. So that's a very nice piece of uranium glass, but a little too big to go in the cloud chamber, so I'm not going to actually put that in. I'm going to take a smaller piece of uranium. I'm going to take a sample. Let's leave it on the Geiger counter for the moment. Let me take a small mineral with some uranium in it. It's called studite. It doesn't really matter what it's called. It's got a little bit of uranium in it. You can tell it's radioactive because if I bring it up to the Geiger counter, okay, it's definitely radioactive. What I'm going to do now is, after looking for a little while at cosmic rays in the cloud chamber, I'm going to place the radioactive sample in the cloud chamber. And if I can do that without disturbing it too much, having opened it up and put the sample in, I've disturbed the alcohol vapor inside. Alcohol is being heated at the top and cooled at the bottom to generate clouds. Perhaps you can see this sort of drizzle, this snow that's falling. That's the alcohol droplets forming. But now that we have a radioactive sample inside, I'm hoping that the radioactive decay of the uranium in that sample will actually show things being spat out from the atoms, things being spat out from the sample. So I'm going to spend the next 30 to 60 seconds waffling until the cloud chamber has settled back down again, and then hopefully we'll be able to see some activity from this radioactive sample. So it usually takes until about now before things have settled back down again. So let's see what's going on. Nothing yet. Okay, sometimes it's up and running in 10 seconds. Sometimes it's taken a couple of minutes. Let's think this is something in between. Again, shout if you see something. As soon as you see something coming out of that sample, give me a shout in case my back is turned when it happens. It might help, I suppose, if I zoom in a little bit. Let me try zooming in. Nothing yet? It's not trying, is it? Yes. Okay. Maybe this is a particular type of uranium that produces clicks in Geiger counters, but not tracks in cloud chambers. I think it's worth persevering because it's quite nice once it gets going. One thing that might be worth doing, if it's not going to play ball just yet, is, was that my imagination or did I just see something? Okay, that's as much waffling as I want to do, so it is now starting to work, and as time goes by, you'll see more and more tracks. And as we watch, now that the cloud chamber has settled after a minute or so, we can see that there are a number of tracks. It might be that you still see tracks that are not connected, don't appear to be coming from the sample. Those are simply cosmic rays in the background. We haven't switched the cosmic rays off. They are there all the time. But now, in addition, we're seeing tracks coming from the sample. Perhaps you notice there are two types of tracks. Do you notice that they fall into two categories, either relatively slim, well-defined, narrow pencil beams, and occasionally rather more ghostly, fat tracks that are less defined. Yeah? So if you build yourself a cloud chamber, or if you invent a cloud chamber 100 years ago, what you realize is that radioactivity is not just one thing. There are at least two different types, possibly more, of particles coming out of this particular rock sample. And if you had different rocks with different elements, you might see a different combination of particles. But we are definitely seeing stuff coming out of this sample. So let me go back to...
Does the sample waste away?
No, it changes. Basically, the uranium is changing into something else, but the same number of atoms are still there. So this is a different sample. This is a sample of boltwoodite, which again contains some uranium. It just happens to be a larger, somewhat prettier sample. This is the one that I actually videoed on my kitchen table, just in case the cloud chamber didn't play ball. But again, you can see that that there are particles coming out of the rock sample, and again, it falls into different categories. If I take a composite image, in other words, take a video and add up all of the frames, then it's perhaps a little easier to see that some of the tracks coming out of the sample are relatively thin, barely 1 pixel or so in this particular presentation, whereas others are very broad and very ghostly. So we have two types of particles. So it's clearly emitting, uranium is clearly emitting something, and two types of something, but what are they and where do they come from? Well, when we look at atoms, this is not a particularly accurate way of thinking about atoms, but it will do for our purposes. An atom is a positively charged nucleus and negatively charged electrons buzzing around the outside. And it's the nucleus alone that's responsible for radioactivity. The nucleus, made up of positively charged protons and neutrally charged neutrons, there will be a different number of those in every atom, and if an atom decides it doesn't like being what it is and wants to change into something else, it's the nucleus that changes, and it's the nucleus that decides this is no longer the same atom. So this is a rather complicated diagram, but let's just imagine we had a very heavy nucleus with lots of protons and neutrons. How might a nucleus change? What might it spit out in order to change from one type of atom to another? It might spit out one of its positively charged protons. It might spit out one of its neutrally charged neutrons. But as well, it might decide that it really doesn't like being what it is, and to make things even faster, rather than spit them out one at a time, it might spit them out as 2 protons and 2 neutrons together. This happens to be a very stable structure in terms of how these things want to bind together. And we either call that an alpha particle, because that's how they were originally discovered. They simply labeled them alpha, beta, gamma types of radiation. So 2 protons and 2 neutrons is simply called an alpha particle, but we now realize that, well, alternatively, we could say, well, that's exactly the same as the nucleus of a helium atom. So we can label them in different ways, and it doesn't really matter how we label them. We're not going to deal with a lot of these things, but let me just say that there are here 2 types of way that a nucleus can spit out an electron. Either the electron that we're familiar with, a negatively charged particle which we would identify as, yeah, that's an electron, the same as any other electron we would know about. But it's also possible for a nucleus to spit out a positively charged, what looks like a close cousin of the electron. It's a positive, or positron, a positive electron. Now, that's actually a particle of antimatter. It is possible for a nucleus to spit out particles of matter or particles of antimatter. Antimatter being similar to matter, but with the opposite charge. We're not going to talk an awful lot about that, but I will mention it again one more time a little later. It's also possible that the nucleus wants to rearrange itself by spitting out a gamma ray. This is rather different from the ones we've been talking about up till now, because the gamma ray is simply a photon, a electromagnetic radiation, an electromagnetic wave, rather than the sort of particles we've been talking about up till now. So we're not going to go into detail about all the possible ways that a nucleus can radiate, but the most common ones that you've almost certainly heard about are the alpha and the beta and the gamma. Alpha rays, let's be clear, an alpha ray is the same as an alpha particle. That's just historical as to whether we call them particles or call them rays. When they were first discovered, they weren't sure what they were, and so everything got called a ray, an alpha ray, a beta ray. We now know they are particles, but the names still tend to rattle around. So an alpha particle is 2 protons and 2 neutrons together, and they are heavy, and they are the bulldozers of the radiation world. When they travel through a cloud chamber, they produce the very broad tracks because they produce a lot of ionization, they produce a lot of condensation in their condensation trail. Beta is effectively shorthand for electrons and their cousins, the positively charged electrons. They're very lightweight, so when we see them in a cloud chamber, they tend to get bounced around by the very heavy atoms that are in there, the carbon, the nitrogen in the air, the alcohol, and so electrons tend to show up in cloud chamber as rather more straggly tracks. And the gammas we're not going to talk about in detail. That's the one you've probably heard of, but it's an electromagnetic wave. It isn't a charged particle. It doesn't show up in a cloud chamber. So if we switch back to what we were looking at just a moment ago, our uranium is now going gangbusters, spitting out lots of alphas and betas, and now we can start to recognize what's going on. Very thin track means an electron, or possibly a positron. It's actually an electron in this particular case. And the very broad, more ghostly tracks that we can see here are produced by the bulldozers, the alpha particles, which are very heavy compared to electrons, so they don't go rattling around and bounce off the various molecules that are in the cloud chamber. They tend to go in straight lines and bulldoze their way through to the edge. Every once in a while you might see a cosmic ray in the background, but there are so many alphas and betas being produced by this sample, then it's quite possible that they get completely lost in the noise of these. So I don't want that radioactive sample in there for later, so I'm going to take it out now and let the chamber settle back down again in the few minutes whilst I continue talking. So let's see if I can get it back out without disturbing it too much. Again, it'll take a few minutes to resettle, but while that's resettling, I will get on with the rest of the talk. So now that we've seen that, we know that the narrow tracks are beta particles and the broad tracks are alphas. So the point is, the cloud chamber, the clicks don't tell us anything, but the cloud chamber allow us to identify what those particles are. That's why the cloud chamber was such an important invention 100 years ago, because it allows you to visualize and figure out what's going on and identify which particular particles you've got. Now, just for the point of, again, context for what comes later, let me just tell you about isotopes. Isotopes are simply cousins of the same type of atom. To make that a little clearer, let's just talk about a particular example. Let's take carbon, for instance. Carbon has got 6 protons in the nucleus. You can turn that around and say any nucleus that's got 6 protons is carbon, because carbon is simply the label we give to any nucleus which has got 6 protons, 6 positively charged particles in the nucleus. If it happens to have the same number of neutrons, so it has 6 protons and 6 neutrons, we call that carbon-12 because 6 plus 6 equals 12. So you are made of lots of carbon and a few other elements. Most of the carbon in your body is carbon-12, but some of it is carbon-14. In other words, with the same number of protons, it must be the same number of protons because it's still carbon, 6. But if it has more neutrons, for instance, if it has 8 neutrons, then 6 plus 8 equals 14. So that's what we would call carbon-14. And I'm not going to take an aside, but you're aware of the fact that carbon-14 is used in radio dating because carbon-14 is radioactive. If it's radioactive and decays, where did it come from in the first place? Well, it's made from nitrogen under the influence of cosmic rays. Cosmic rays hit nitrogen in the atmosphere and generate carbon-14. And then we can use carbon-14 for dating organic materials, because generally speaking, carbon gets taken up, carbon-12 and carbon-14, when an organism is alive. Now, in terms of the radioactive elements that, well, some of which you've heard of, I'm sure you've all heard of uranium, but perhaps you weren't aware of the fact that potassium is actually one of the most abundant of the radioactive elements. Even though there's a fair bit of potassium in us and pretty much everything we eat, it is actually radioactive. For instance, in your body, if you calculate it, the number of potassium atoms that are decaying each and every second of the day is about 4,000. And if that sounds scary, the fact that 4,000 potassium atoms are decaying into something else and spitting out radiation, remember that is a tiny number compared to the number of atoms in your body, which is a huge number with far more zeros than just the 3 that we've got there. And potassium is one of the largest contributions to radiation. The other contributions are 2 elements which you may have heard of. Thorium is actually more abundant than uranium, even though you might not have heard of thorium, but you have heard of uranium. Not only is thorium more abundant, but uranium is more abundant than you think as well. It may be surprising to realize that uranium is actually 500 times more abundant than gold, for instance. It's just easier to pull gold out of the ground than it is to dig uranium out of the ground and purify it. So it's only a few parts per million, but that's a huge amount compared to various precious metals. In the Earth's core, these elements, potassium, thorium, and uranium, are decaying, producing particles, producing energy, producing heat effectively, and that is keeping the core of the Earth warm. It is keeping it molten. And if you have a molten core, a rotating metal core that's made of liquid, you've got a dynamo, so you've got the Earth's magnetic field. So it's an interesting sort of, not irony, but it's an interesting cycle of life that radioactivity keeps the core molten, which produces a magnetic field which helps protect us against some of the radiation that's raining down on the Earth. So it's a sort of circle of radiation in that sense. And as an aside, it might be that Mars has got no atmosphere because it lost its magnetic field, because it lost its molten core, because it is a smaller planet, it cooled down faster, and that's why Mars is rather different from the Earth. Just again, as a sort of aside, just before we get back to cosmic rays, a very small amount of potassium is called potassium 40. The 40 simply refers to how many protons and neutrons in total in the nucleus. And that particular isotope of potassium emits beta plus radiation. Beta, electrons and its cousins, but the plus indicates it's not an electron, it's the positive equivalent of the electron, the positron, or antimatter. So basically, anything with potassium in it emits antimatter. So any food rich in potassium, like Brazil nuts or bananas, actually emits antimatter. And that led to the idea of the banana equivalent dose. If you're thinking about how much dose you get from various radiation sources, you can always equate it to, well, bananas produce antimatter radiation. How much does any particular source generate compared to bananas? So it's sort of serious, but it's actually a useful way of getting an idea of low-level doses of radiation. And again, we're still clicking, so let me just kill that for the moment. For instance, if we wanted to say, well, cosmic rays are arriving in this room and going through the room, going through the cloud chamber, going through the Geiger counter, how much does everybody receive as a dose from cosmic rays? If I gave that in physics units, it would mean nothing to you, but we could give it in banana equivalent doses and say, how much do you receive from cosmic rays compared to eating 1 banana? And the answer is cosmic rays every day is equivalent to something like 2 hands of bananas. In other words, it's 10 times the amount. Bear in mind it would have to be doubled or more if you spend a lot of time in aircraft at altitude, simply because you are closer to the source of cosmic rays. This is why pilots have to be careful if they are flying at altitude a lot of the week or the month. You have to add up a pilot's hours to make sure they don't receive too much of a radiation dose. And finally, before I finish terrestrial sources of radiation, bear in mind not all radioactive sources are like the ones I've got in the front here. They're not all necessarily solid lumps of rock. Some of them are in gas form. So radon, for instance, is a radioactive gas formed by the radioactive decay of uranium. Uranium tends to occur in granite-type rocks, and granite is pretty much everywhere. But certainly uranium is everywhere, even in tiny amounts. If we look at radon concentrations, we find that it follows effectively where most rock formations are. If we look at Cambria, Cumbria, the Pennines, the Southwest, etc., we find radon concentrations are high in those areas simply because the uranium concentration is high, generally because the granite concentration is high. And if we think of where radon emits its particles, it emits its particles as alpha particles. It's a daughter of uranium. It spits out alphas when it decays. And alphas don't travel very well, don't travel very far through materials, which means alphas can't actually get through a piece of glass like the cloud chamber. So if we ever see an alpha in a cloud chamber, it can't have come from outside because it can't have got through the glass. If we see an alpha in a cloud chamber, that means we're seeing an alpha radiation from radon gas, because there is radon gas in this room. In a room this size, there might be 1 billion atoms of radon. Again, that sounds like a lot, but it's tiny compared to the number of molecules of nitrogen and oxygen, etc. So I've spent a little too long talking about the background, so let's get a move in and talk about cosmic rays. These are the pioneers of radiation. Perhaps you recognize Marie Curie in the middle. You might recognize Becquerel on the left. You probably don't know Victor Hess on the right-hand side. It was well known at the end of the 1800s, when people were dabbling with radiation, that there was such a thing as background radiation. They had electroscopes. These are electrometers. Basically, you charge them up. It's a couple of leaves of gold leaf. And when they have a positive charge or a negative charge, like charges repel, so the two leaves diverge from each other. But it was noticed that they would often collapse, implying that there was some additional positive or negative charge getting into their electroscopes. Where's this positive or negative charge coming from? The bottom line is it coming from above or is it coming from below? There appears to be always some background radiation. In order to answer the question, is it coming from the Earth or is it coming from the sky? Well, in 1910, Theodore Wolff said, I know, I'll take an electroscope to the bottom of the Eiffel Tower and see how much radiation there is there. Then I'll go to the top of the Eiffel Tower and see if it goes up or goes down. Right idea. But it really didn't change enough to be sure. The experiment wasn't accurate enough to tell exactly what was going on. Question, has it been complicated by the fact that the Eiffel Tower is radioactive? Well, that's not a silly thing to consider, because the Eiffel Tower is made of iron. Iron is dug out of the ground is radioactive, so maybe the tower is. Also, we know that radon exists, so is it possible that the atmosphere radioactivity is affecting the measurements? This is where Hess steps in and said, the Eiffel Tower isn't high enough. If you want to tell what's going on, you need to go higher than the Eiffel Tower. So basically, he built himself detectors that would, allow balloon flights to take his detectors up to various altitudes and still work even at thousands of meters, so that he could tell whether or not the radiation goes up when you go in altitude or goes down when you go up in altitude, thus telling you whether the radiation is from the Earth or from the sky. So in 1911, he took a balloon flight to 1,000 meters and he determined, well, not much. The radiation levels didn't seem to change so much, which is why the Eiffel Tower wasn't high enough, because even 1,000 meters isn't really high enough to tell what's going on. But the following year, he took a balloon to 5,000 meters, and then the radiation levels increased dramatically. So that's why Hess gets the credit for discovering cosmic rays. He basically proved that if you go high enough, the radiation levels go up substantially, showing that the radiation is coming from above, not from below. Yes, the Earth is radioactive, but generally speaking, that's a tiny amount compared to that coming from the sky. Hence, when we switch the Geiger counter on, we're not really picking up anything from the Earth beneath our feet. We're picking it up mainly from the sky above us. But still the question, it's coming from above us, but is it coming from the sun, or is it coming from somewhere beyond the sun? Again, a perfectly sensible question. How do you decide? Well, having taken a balloon flight to measure radiation, you could then say, well, easy, you just take a flight at night when there's no sun in the sky. Who wants to take a hot air balloon up at night where you can't see where you're going, you're at the mercy of the wind, and you can't see where you're going to land? So nobody wanted to do that. So Hess had a brilliant idea. You take the balloon up on the day of a solar eclipse. fantastic. You take it up, you measure the radiation, you wait for the moon to block the sun. The moon surely is big enough to block any radiation from the sun, and you see if the radiations go down or go up. And the answer is they did neither. So the sun is not a significant source of cosmic radiation. It does produce some, but most of it is coming from elsewhere beyond the sun. That's why in 1936 Hess got the Nobel Prize for discovery of cosmic radiation, this set of balloon flights that showed that the radiation is cosmic. So this is not a good artist's impression for a number of different reasons, but it gives us an idea of what's actually going on. Some charged particles are hitting the Earth's atmosphere. They're raining down on the Earth's atmosphere all the time. And if the particle has a lot of energy, it produces a shower, a cascade, an avalanche of secondary particles, a so-called air shower. So we don't yet know what those particles are that's arriving, but what we can do is measure what's going on in terms of what reaches ground level, which is, of course, the clicks in the Geiger counter and the tracks in the cloud chamber. So this diagram on the right-hand side is a little bit simplistic. There's far more going on than this diagram would indicate, but at least it shows that an incoming primary cosmic ray coming from somewhere in the universe is hitting the Earth's atmosphere, hitting a nitrogen atom or an oxygen atom, producing secondary particles which eventually make it to the ground level. At each level of this cascade, new particles are created and they share the energy of the particle that created them. So it might be that one comes in, it might be that hundreds, thousands, or even millions of particles end up at ground level, but they each share some of the energy of the incoming particle. What sort of particles arrive down here? What sort of particles are we actually seeing in the cloud chamber? Some of them we're familiar with, like protons and electrons. They make us up anyway. They make up atoms, so we're familiar with protons and electrons. But some of the particles generated in a cosmic ray shower are nothing whatsoever to do with atoms. They are particles that apparently exist in cosmic ray showers, but wouldn't exist otherwise. They are, in a sense, new particles, and many of them are unstable. Some of them don't live for more than a tiny fraction of a second. Some of the particles we were watching over coffee before the talk started might only live for a few millionths of a second. So by the time we've seen them in the cloud chamber, they've changed into something else. They've decayed into a different type of particle. One such particle is called a muon. It's similar to an electron in the sense it's a sort of distant cousin to an electron. It's got the same charge as an electron, but it's much heavier. It's 200 times heavier. So when we see what's going on in a cloud chamber, an electron is very light and will tend to rattle around and produce a very straggly track, whereas a muon is much heavier and they will tend to produce much straighter tracks. So a muon is nothing to do with atoms. Atoms, remember, protons, neutrons, and electrons. Muons are something different. A muon will only live for a few microseconds, but that's pretty much enough time for them to get from the upper atmosphere down to ground level for us to detect them. That's just as well, otherwise we'd never be aware of their existence. So that's what a muon looks like. There's a picture I took. I've enhanced it to make the contrast a little bit higher. There's what you would expect to see in a cloud chamber, the black background, and then this row of droplets, a relatively straight line, indicating that a muon has passed through the cloud chamber here. But we've been talking about secondaries, what arrives at the Geiger counter, what arrives in the cloud chamber. But what's coming in at the top? What's coming in? What are the primary particles that are generating the showers in the first place? Well, a few decades research since Hess made his discovery in the early part of last century has told us that the incoming particles that are responsible for cosmic rays are mainly protons. 90% of them are protons. If you wish, you can think of them as the nuclei of hydrogen atoms, because a hydrogen atom is just a proton with a single electron. 9% of cosmic rays coming in, hitting the atmosphere, are alpha particles. These are the ones that we know about, 2 protons, 2 neutrons, otherwise known as the nucleus of a helium atom. And the remaining 1% is a mixture of loads of other things, a few electrons and a few nuclei of heavy atoms. In other words, which atoms? Well, all of them, essentially. If you think of all the atoms that we see in the solar system, lithium, beryllium, boron, carbon, nitrogen, oxygen, all the way up to the most of the periodic table, it looks like cosmic rays are the same. They are the nuclei of all of those same elements. So we think those elements exist across the Milky Way and presumably elsewhere as well. And it looks like cosmic rays are positively charged nuclei of atoms across the spectrum, across all the masses, and something is accelerating them and sending them towards Earth, where they crash into the atmosphere and produce cosmic ray showers. So how do we go about detecting them? We've got an idea of how we do it at ground level. We know about this Geiger counter. How does a Geiger counter actually work? It's a relatively simple device. Remember, we should be calling them Geiger-Müller tubes, but let's not worry about that. Inside the detector itself, it's a cylinder with gas, some inert gas, maybe helium, maybe argon. Radiation comes in, ionizes the gas inside. If you ionize an atom, you free an electron from the positively charged ion that's left. So if you apply a high voltage between the inner electrode and the outer case, the atom will go one way, the electron will go the other way, and you'll get a current. Ionization will lead to a current if you apply a voltage, and if you measure that current, the yellow box basically just measures the current and produces a click whenever the current goes up. So it doesn't tell you what has produced the ionization. As its name implies, its colloquial name of Geiger counter, it simply tells you how many have arrived per second to give you an idea of the total arrival rate. Cloud chambers are rather different. Where did cloud chambers come from? Well, back in the early part of the last century, inspired, it is said, at the end of the 1800s by the sight of a Brocken spectre at the top of Ben Nevis, Charles Wilson looked on a misty day. The sun was behind him, and he saw the Brocken spectre, his shadow with a large halo around it. He thought, this is worth studying. I'd like to know what's going on, how you get these optical effects in moist air. I don't want to put my laboratory on the top of Ben Nevis. I want the cloud to come to me rather than me to go to the cloud. So what I want is to be able to make a cloud in a jar in the lab. So he basically decided that he would make a cloud chamber. And he did that for the purpose of studying clouds, or at least studying optical phenomena in clouds. And in 1911, he produced the first cloud chamber. But it wasn't long before he realized that something is getting in the way of me making these clouds. I keep seeing lines. Every once in a while, I see something coming through my cloud chamber. It looks like I'm seeing some background radiation. And as soon as he basically realized that, then physicists jumped on this and said, this is, okay, useful for looking at optical phenomena in clouds, but look, it's really useful for looking at charged particles. We can do fundamental physics by looking at the tracks generated by particles traveling through a cloud chamber. Not only can we tell what type of particle they are, as we've seen in the cloud chamber at the front here, we can see how much they bend in a magnetic field, which tells us how much energy they have, and we can talk about the types of particle, identify the particle, the energies of the particle, the interactions between particles. We can learn a lot more about how the world is put together using the cloud chamber as a particle detector. That wasn't what Charles Wilson had in mind, but that's what it became famous for. In 1927, he was awarded the Nobel Prize for what was quoted as the most original and wonderful instrument in scientific history. That's an amazing quote for any particular object, let alone a rather humble cloud chamber. So in 1911, it looked like that. In 2024, it looks more like this. Yes, I know that my cloud chamber looks more like a cafetiere, especially if NASA decided to land a cafetiere on the moon. That's what it would look like, yes. But if you're going to build one for a few tens of pounds, that's the way to do it with modern technology. Details are at the front there if you want to try it for yourself. So I'm not going to talk about the construction. That's what it looks like in section. That's what it looks like on the front bench here. The idea is you set it up in such a way that you have a heater at the top to generate the alcohol is on a sponge there. You heat it up such that the alcohol evaporates. It is a refrigeration unit and a heat sink and a fan at the bottom to keep the bottom cold. clouds will form, or at least drizzle will form, of the droplets, and above that black plate, which you can see here, this sort of rectangle here, above that black plate is where the particles will be visible. So let's switch back to our demo, and we may or may not see it playing ball. Again, if it helps, let me zoom in a little bit. Let's just give it a minute or two and see if we get some cosmic rays coming through. The radioactive sample, I have taken it out. Let me be absolutely sure by moving it away from the cloud chamber that there's no radioactive sample anywhere close to the cloud chamber, and so anything we see now must be cosmic rays. Or occasionally we might see an alpha indicating that we've got some radon in there. So we saw a little track there, a little one on the right-hand side. I saw one earlier just as I was putting the samples away. There's a little one in the middle there. If cosmic rays come in sideways, we might get a nice long track. If they come in vertically, then the tracks are very short, and sometimes you just see a flash of light. There was a nice track on the left-hand side there. I hope you all saw that. What else have we got going on? Again, let's just give it a minute or two so that we can see something. It's about time we had a nice muon coming through. Like buses, you wait for ages and then 3 come along at once. At the moment, we're just seeing a little bit of pulsing in the cloud that's drizzling down onto the base plate. There was a nice one. That was a muon going vertically through the screen as we look at it. Just a few more seconds to see if there's another one. There was a nice one, another muon coming through. So again, just in case the cloud chamber didn't play ball or was too difficult to see, let's go back to the PowerPoint. I made a video earlier, again, when I had it running on my kitchen table, and what I did was take a video of lots of tracks coming through. That was a nice proton coming through on the right-hand side there, a nice, bright, obvious track. I videoed it for quite a while, possibly about an hour or so, and then I took all of the tracks that I could see and simply made a composite of all the tracks that are seen over a period of about an hour. And that's what you would see if you had the patience to wait long enough. The very bright ones are protons that have come through. The not so bright ones but straight lines are muons, and sometimes you see extremely wiggly tracks. Those are electrons. I have not showed any alphas here because alphas are not coming from the cosmos. They can't get through the glass. They could get through the building, but they can't get through the glass. Sorry, they can't really get through the building. They can get in, they can move through the room, but they can't get through the glass of the cloud chamber. So they are not coming from outside, and so I haven't included in this composite as these are only cosmic rays. Muons, electrons, protons, possibly other things, but relatively low numbers of anything else. So over a period of an hour, I think I saw many, many hundreds of tracks. And here I've just shown some of the longer ones rather than a lot of the shorter tracks. In terms of trying to identify the primary particles, remember the ones that are hitting the top of the atmosphere, we can't do that from ground level. We'd have to go above the atmosphere to see the primaries, which is why they've got detectors on, for instance, the space station. So that gives you an idea of the size of this particular cosmic ray detector. There's an astronaut above left, not necessarily fixing it, but just in the shot to give you scale. So there are detectors on the ISS, and we have a number of different detectors at ground level. So ground-based observatories, one of the biggest of them is the Pierre Auger Observatory in Argentina. So remember, we've got a particle coming in producing a shower, and in order to catch as many of those secondary particles as possible, we want the detector to be as huge a footprint as possible, because this shower could be over many, many kilometers. So to catch a reasonable fraction of the particles produced in a shower, it was decided to build this observatory in Argentina, where there's a lot of spare land, and I'm sure from this map you can't tell what the footprint is in terms of how many kilometers this is spread over, but these detectors, these tanks that I'll come to in just a second, are spread over an area approximately the size of Luxembourg. Okay, that gives you an idea of how big this observatory is. So these tanks are picking up the secondary particles as they pass through. In the cloud chamber, we see them and can photograph them. but these tanks here are all enclosed. So how can you tell if a cosmic ray has passed through this tank? The tank is actually full of water, and you can actually use water or other transparent media, such as, well, solid water, ice, or you can use air, and you can tell if a cosmic ray has passed through because of the phenomena that you're probably familiar with. If you have an aircraft traveling through the air faster than sound can travel through the air, what do you get? You get a shock wave. You get a sonic boom. You can see the shock wave produced by the way the water is condensing here. So if an aircraft traveling through the air faster than sound travels through the air gives you a sonic boom, what happens if a particle travels through a transparent medium faster than light can travel through that medium? Nothing can travel faster than light in a vacuum, but when you're traveling through air or water or ice, it is possible for a very energetic cosmic ray to travel faster than light can travel through that same medium. So instead of getting a sonic boom, you get the optical equivalent, a photonic boom. And this little animation shows what's going on. If a particle comes in at the top, it produces secondary particles, and the secondary particles produce a cascade of high-energy particles. If they're traveling faster than light can travel through the air, for instance, then we get a photonic boom. We get a flash of blue light. It's called Cherenkov radiation or Cherenkov light. This is very slowed down because this happens in about a billionth of a second. But the cosmic ray shower that's generated produces a blue flash. And telescopes can look into the atmosphere. The Cherenkov telescope array, part of which is in Chile and part of which is in the Canary Islands, has been set up to look for the blue flash, indicating that cosmic rays are coming into the atmosphere. The blue flash is nothing like as bright as this animation would have you believe, which means you need large telescopes. Here we see a number of different telescopes are being built in the Canary Islands and in Chile. Only a few of them have been built so far. It's an ongoing project. It'll take many years before all of these telescopes are built. But they're not looking for the sources of the light. They're looking for the light itself. And hopefully they can figure out if the light has come in and we see the light in a shower, then where must the particle have come from? Let's trace it back to figure out where that cosmic ray has come from. In addition to doing that in the water tanks of the Pierre Auger Observatory, in addition to looking into the sky for the Cherenkov telescope array, it's possible to do the same thing in water that's been frozen. At the South Pole, there's a laboratory sitting on top of the ice cap. There's the top of the ice cap. There's the Antarctic bedrock. And just to give you an idea of scale, there's the Empire State Building. So there's 2 kilometers of ice that they have instrumented by drilling into the ice and putting a load of photodetectors in there. They've instrumented 1 kilometer by 1 kilometer by 1 kilometer, the world's largest ice cube, which is why it's called the Ice Cube Laboratory. And the intention is that if any particle comes through the ice cube, those photodetectors will see the blue flash. And if you look at which detectors saw the blue flash, you should be able to work out where that particle came from. And by looking at how bright the Cherenkov radiation is, you should be able to tell how much energy was being carried by that incoming particle. So that's the idea of using these ground-based observatories. The final section, which I'll finish in the next 10 minutes, is, well, great, okay, lots of these things are arriving. We can see that from an amateur's cloud chamber or from some very sophisticated ground-based observatories looking into the sky, looking at water, looking at ice. But where do they come from in the first place? Where are they coming from? And given that some of them are very energetic, we see millions of secondary particles. So how energetic was the particle that came in that gave all these particles their energy? Where did they get their energy from? Well, let's just remind ourselves that it's about 100 years, give or take a few weeks, since Hubble said back in 1924, a few months yet, but late in 1924, he was looking at these spiral nebula in the Milky Way. What are these smudges of light that we see? Are they actually in the Milky Way, or are they actually bigger and more distant? By looking at variable stars, he was able to determine the distance to these spiral nebula, and he showed that it was confirmed that these spiral nebula are actually stellar systems, what we would now call galaxies. They are galaxies in their own right. They are not small smudges sitting inside the Milky Way. The entire universe is not just the Milky Way. Apparently, these smudges are galaxies in their own right, and we now know that there are some trillion or galaxies that we know about, and who knows how many we can't see. So the universe is a lot bigger than was first thought. This was the nail in the coffin of the great debate that took place in the 1920s, where people were trying to work out, is the entire universe just the Milky Way, or are there things beyond the Milky Way? And we now know the universe is much, much, much bigger than was first appreciated. So remember, Hess, in his historic balloon flight experiments, has already shown that if you take a balloon flight, the eclipsed sun doesn't seem to make any difference. So we know they're coming from more remote than the solar system itself. But are they coming from the Milky Way or somewhere else? Hubble's observations in the 1920s has told us that the universe is a lot bigger than just the Milky Way. So the question can be rephrased. Are cosmic rays galactic? Are they coming from the Milky Way? Or are they extragalactic? Are they coming from somewhere outside the Milky Way? What's the origin of these lines that we see in the cloud chamber? Well, some people say, well, it's got to be supernova. Yeah, the answer is always supernova. Supernova produce shock waves when a massive star comes to the end of its life. It ejects a lot of material, essentially all the material of the star. It produces shock waves, and maybe those shock waves can accelerate charged particles, and that's what we're seeing raining down on the Earth. Anybody who doesn't think it's a supernova says it's a black hole. The answer is always black holes. If it's not supernova, it's black holes. And we know that jets from supermassive black holes, we think supermassive black holes exist at the center of every galaxy, our own, and as far as we can tell, every other galaxy we look at. So maybe it's the shock waves produced from supermassive black holes. I'm not going to talk through this diagram on the right because we're not even sure it's correct or not. Some people are saying, yeah, a shock wave could in principle accelerate charged particles to very high energies. But we're not exactly sure why, and we're not exactly sure how. So theorists can come up with all sorts of ideas, but we are severely lacking in terms of data to tell us whether or not that's actually the case. But surely we should be able to work this out. Shouldn't we just be able to look at a cosmic ray shower, work out where it's come from, and it points back to where it came from? Isn't that easy? If we look at enough showers, surely we just trace back and say, oh, that's what produced it. It's that supernova there, or that galaxy, whatever. You'd think that would be relatively straightforward. We've done that with telescopes looking at light traveling across the universe. We can look at light that's traveled for billions of light years. Why can't we do it with cosmic rays? Well, it's not quite so simple with cosmic rays because they are charged particles rather than just light. And charged particles are deflected by magnetic fields, a fact of life and most physics undergraduate laboratories. Magnetic fields, unfortunately, are everywhere, and therefore we can only work out whether or not this charged particle came from a particular location if we know what magnetic field it's passed through. If it's passed through a strong magnetic field, it would have been deflected. So it might appear to have come from over there, but it actually came from over there somewhere. We could be completely wrong. Magnetic fields, we know about magnetic fields around the Earth. Any particles, any low energy particles that come close to Earth will end up spiraling in the Earth's magnetic field, and that might be why we end up with some aurora getting channeled into the north and south poles by the Earth's magnetic field. More energetic particles don't necessarily care about the Earth's field, but they will care about magnetic fields on their journey from wherever the source was to here on Earth. Now, in terms of working out what magnetic fields exist, with a bar magnet in the laboratory, it's easy to work out what the magnetic field looks like. We just sprinkle some iron filings down, and then we see the magnetic field. We can't do that with the galaxy. Well, we can sort of do that with the galaxy. We can't use iron filings, but we can use dust. And people have actually mapped out the polarization produced by dust. Dust, generally speaking, small particles, tiny micron-sized particles of carbon and silicon and maybe a few other bits and pieces, they tend not to be spherical. They tend to be slightly elongated, which means if there is a magnetic field, they tend to line up. And so if you look at polarized light scattering off dust, you can get the hint of the magnetic fields inside the Milky Way galaxy. And the bottom line is they appear to be quite chaotic. They're nowhere near as simple as the Earth's field, which is complicated enough. And so we have great difficulty in figuring out what the magnetic field in the Milky Way is. What the magnetic field outside the Milky Way is even more of a mystery. So how can we possibly work out where these particles have come from? The only saving grace is, again from basic physics, the more energetic the particle, the less it's going to be deflected. So even if these magnetic fields are out there, if we look at only the most energetic particles, hopefully we can trace them back to their source. Now, the most energetic particles, just to give you an idea, I'm not going to explain all the details, but if we just take a unit of energy called an EV, the photons that are hitting my hand from the projector are photons of visible light. They have an energy of about 1 EV. We won't worry about it, we'll just use that as a basis. If we go 1,000 times more energetic, we get very energetic photons, such as, for instance, X-rays. They are more penetrating because they are 1,000 times higher energy than the photons of visible light. If we go to 1,000,000 times that energy, we get the sort of energies that alpha, beta, gamma, the sort of energies that were coming off these radioactive samples that I showed you earlier. But if we want to deal with cosmic rays, we apparently have to deal with much, much, much higher energies. Billions, trillions, quadrillions of times the energy of a photon of visible light. And just to give you context, the Large Hadron Collider is colliding particles with this much energy, as indicated by the left-hand arrow. And if they ever get enough money to build the next generation of collider, called the Future Circular Collider, that will have an energy given by the right-hand arrow. You can see that the energies of some cosmic rays are much, much, much higher than anything we can generate here on Earth. And let's not worry too much about the details, but if we look at how many particles arrive as a function of their energy, we think the lower energy stuff might be coming from the sun. The middle energy stuff we believe is coming from the Milky Way galaxy, and the most energetic particles, it is believed, are coming from other galaxies in the universe. But the number that arrive is part of the problem. There might be 1 per square meter per second. That's the number arriving at the top of the atmosphere. Remember, the Earth's atmosphere is a huge number of square meters, so that's a lot of particles. But if we go to the higher energies, the flux has dropped off considerably. If we're looking at the higher energies, only 1 per square meter per year compared to per second. And if we go to the extreme energies, the so-called ultra-high energies, there we have 1 per square kilometer per year. 1 per square kilometer, not per square meter. And therefore, we have, in principle, very high energy particles hitting the Earth's atmosphere, but it's very rare in the sense we need to do experiments for many, many months, if not years, in order to see very high energy events. But we have seen high energy events. For instance, a telescope this isn't in Argentina, this one is in the USA. This was reported in the Astronomy Picture of the Day a few months ago, based on data they took many months earlier. They deduce from this artist's impression that a very high energy particle came in and produced a lot of secondaries, some of which were recorded by their array here. It was the second most energetic event ever discovered. The most energetic event was called the oh my god particle, because when the scientists first saw it, they could not believe that one particle could carry so much energy, and they're still struggling to understand how can it get so much energy in the first place, and how can it arrive at Earth not having lost any of that energy. This was the second most energetic event of a few months ago, called the Amaterasu event. Amaterasu is a Japanese sun god, meaning shining from heaven, or something like that, so very apt. And the Amaterasu event should not be confused in any way with the tiramisu event, which is what they had at the party afterwards. So the Amaterasu event was a very energetic event, so in principle, if you detect what's going on at ground level, figure out what's going on, figure out how much energy was dumped, backtrack it, and find out where this particle came from. Where did this really, really energetic particle come from? Well, we hope that they would have despite the magnetic fields that permeate the Milky Way and elsewhere, we hope that they should be deflected very little. So tracing back from the Amaterasu event should tell us the origin. So they did that. And they traced it back, and the direction they found points to, pause for dramatic effect, nothing. They could not identify any supernova which could have been the origin of that event. They could not identify any galaxy with a supermassive black hole which could have been the origin for that particular particle. So something is wrong. Either supermassive black holes and supernova are not the sources and there's something else there that's producing these particles, or the magnetic fields out there are stronger than we reckoned and they are deflecting the particles, even these really energetic ones, to the point where we can't simply trace back to where they come from. The bottom line is we need more data. We need to run these observatories for longer to get more data to try and figure out, have we got the sources wrong, or are magnetic fields scrambling the paths of these particles to the point where we really don't know where they're coming from. Let me finish with just an indication of how energetic these particles are. I said the scientists couldn't really believe just how much energy these things were carrying as a single particle. Let me give you an idea by just relating it to something we can perhaps get our heads around just about. How energetic? Well, remember, the more energetic a particle is, the closer it's going to travel to the speed of light, and vice versa. The closer it travels to the speed of light, the more energetic it has. Now, we know that no particle can travel faster than light in a vacuum, but what sort of speeds are these things traveling at? From the observations made, you can work out the energy of the particle that hits the atmosphere. And they've calculated, as a percentage of the speed of light, how fast the oh my god particle was traveling, which is roughly the same as the speed of the Amaterasu particle. Turns out to be, as a percentage of the speed of light, these things are traveling at 99.9999999, not done yet, 999, still not done, 999, nearly there, 999,995% of the speed of light. That's how fast these things are traveling. How can you accelerate something to that speed? That is still a mystery. And those nines, even if you count them, it's difficult to get your head around what that means. So let me finish with just a visualization of what we're talking about. Imagine, hypothetically, a race through perfect vacuum between one of these cosmic rays and a photon of light. We're going to have a race that is 100,000 light years long from start to finish, roughly the size of the galaxy, roughly speaking. The cosmic ray and the light are going to leave the start line at the same time. Now, we know light is going to win because this is a race in vacuum and the cosmic ray can't travel at the speed of light or faster than the speed of light. So the light will cross the finish line first. When the light crosses the finishing line, how far behind it is the cosmic ray, which has been lagging because it's not quite traveling at the same speed? After a race of 100,000 light years across the galaxy, the cosmic ray will be behind the light beam crossing the line by approximately 5 millimeters. That gives you an idea of just how fast it's going. It only lost ground by 5 millimeters over 100,000 light years across the galaxy. If you think of it in terms of time, if you click a stopwatch when light crosses the line and then click the stopwatch again when the cosmic ray crosses the line, what's the time interval after a race lasting 100,000 years? The time interval would be less than a nanosecond between the two. And again, just trying to understand what mechanism, what process accelerates particles to that sort of speed is still a little bit of a mystery. So the bottom line is cosmic rays, well, they're interesting for quite a few reasons. They are accelerated, these particles are accelerated somewhere, somehow. We don't know where, we don't know how. Somehow they get these enormous energies. Perhaps supernova and supermassive black holes are sources. They are probably sources, but we are not absolutely sure. Maybe there are other sources that we haven't thought of yet. Maybe there are some violent processes in the universe which are capable of accelerating particles to these sorts of speeds. We know that in principle they're deflected by magnetic fields. We know that low energy stuff will get their paths scrambled, and we don't know where they're coming from. We hope that the highest energy particles, we have a chance of tracing them back on straight lines to see where they came from. Some particles make it past Earth's magnetic field. We know some of them do because we can basically detect them. Hitting the atmosphere produces an air shower of secondary particles, and some of those secondary particles make it to sea level. Not necessarily all, but a fair fraction of them make it to sea level. And those that do, including muons, electrons, protons, they make clicks in Geiger counters, and they make tracks in cloud chambers. And that's what we've been seeing this morning. So that, remember, is a composite of lots of different cosmic rays. We seem to have lost the clicks. Oh, well, never mind. So remember, these cosmic rays that we see and have been seeing for most of this morning, they might have started their life in a supernova in our Milky Way. They might have started their life in the jets of a supermassive black hole in another galaxy. But regardless, when you look in a cloud chamber, when there's no radioactive samples around, you're effectively looking at the cosmos in action. Thank you all for listening.